Hello everyone, welcome you back. In today's class, we are going to study transportation problems, which is a special case of linear programming problem. And the discussion will be with respect to a non-degenerate initial basic feasible solution. So what is a degenerate basic feasible solution and what is a non-degenerate basic feasible solution? We will understand in the subsequent slides. So let's start. Now, a transportation problem is a problem which deals with transporting various quantities of a single homogeneous commodity from different sources to different destinations in such a way that the total transportation cost is minimum. Right? So what do we mean by this? See, there are various sources. As we can see here, we have got m sources starting from 1, 2 up to m. And similarly, we have got various destinations like 1, 2 up to n. So the goods are being produced at these sources, and each destination may be considered as a warehouse where the goods are to be transported. The supplies at various sources are given by S1, S2 up to Sm, and the demands at the destinations are represented by the Ds. So D1, D2 up to Dn, they represent the demand at various destinations starting from 1, 2 to n. Okay. Now here what we will be mentioned in the what we will be provided with is the CIJ. CIJ stands for unit transportation cost, that is to transport a single commodity from a source I to destination J. Always remember the first subscript in the CIJ represents the source and the second subscript represents the destination. So CIJ represent how much company has to bear, how much cost the company has to bear to transport a single commodity from a particular source I to a particular destination J. Okay. So all the supplies will be mentioned to us, all the demands or the requirements at various destinations will be provided. CIJ will be provided from various sources to various destinations. What we are asked to find out is XIJ. XIJ means X represents the quantity. So quantity to be transported from a particular source I to particular destination J, that is to be found out. Okay. So let's see. This is the structure of this is a matrix structure of a transportation problem. As you can see, we have got four sources F1, F2, F3, F4, and we have got three destinations D1, D2, D3. Right? Now the supply at various sources are A1, A2, A3, A4, whereas the demand at each destination are B1, B2 and B3. As we have mentioned, the unit transportation cost figures will be provided with. So suppose if I say C21, that means what is the unit transportation cost or to transport a single commodity, how much cost has to be borne to transport a single commodity from source F2 to destination 1, that is C21, right? Similarly, C43 represents the cost to be borne to transport a single commodity from the source F4 to destination D3, right? So that is what will be mentioned to us. So we can see transportation is a special case of linear programming problem which involves a number of shipping sources and a number of destinations. Okay. Each shipping source has a certain capacity, that is A's, and each destination has a certain requirement, that are B's. Now each element in the transportation matrix represents the cost associated with shipping unit commodity from a source to a destination. That's what we have seen. So all these represents the unit transportation cost. C's represents the unit transportation cost to transport a single commodity from a particular source to a particular destination. The objective is to minimize the transportation cost. Definitely, when we are dealing with cost, we would like to minimize our transportation cost, right? And finally, total supply at the sources must be equal to the total demand at various destinations. That means summation of A1, A2, A3, A4 should be matching with the summation of B1, B2, B3. Then we say the matrix is a balanced one. By any chance, if the matrix is not balanced, then we have to balance it first before we proceed further. So suppose summation of A1, A2, A3, A4 is more than the summation of B1, B2, B3. That means what we have to do? Matrix is not balanced. So since this side is coming less, so we should add a dummy column, right? With its requirement being the difference between summation of supply minus summation of demand. So that is how we add a dummy row or dummy column as the case may be if the matrix is not balanced. Now, since transportation is a special case of a linear programming problem, so it has got a special technique to solve such problem. Now, such technique has got two sub-steps or two steps. First step is to get the initial basic feasible solution. So first we have to get a solution, right? Initial solution. Now, if I'm sure you remember what is a solution. A solution means which satisfy all the constraints, and it is called feasible solution if it is called if it satisfies the non-negativity constraint, right? So that is the initial basic feasible solution we will get. And second step is to obtain an optimal solution or the best solution from this initial basic feasible solution. Okay. So any transportation problem when we are asked to solve, then first step definitely is to see whether the given matrix is a square one. If it is square one, well and good. If it is not a square one, add a dummy row or dummy column as the case may be. And then you solve to get the initial basic feasible solution. And finally, you obtain the optimal solution from the initial basic feasible solution. Okay. So there are three techniques by which we can get initial basic feasible solution. One is northwest corner method. Second is least cost method, and third is Vogel approximation method, which is also called VAM method. And this VAM method gives you the best initial basic feasible solution. And the northwest corner method gives you the poorest basic feasible solution. So if nothing is mentioned regarding the technique by which you have to get the initial basic feasible solution, in that case it is always preferred that you apply Vogel approximation method because that gives you the best solution. Okay. So the first step in the transportation problem, as we have said, is to ensure that the transportation matrix is a balanced one. If it is not balanced, we cannot proceed further. Now, how to balance transportation problem? This we have discussed once more. If total demand is more than total supply, that means summation of B1, B2, B3, these are the demands. So summation of B1, B2, B3 is more than the summation of A1, A2, A3, A4. Definitely, in that case, what you have to do, since this is more, that means A side is coming less, so you have to increase A. That means you have to add a dummy row. Dummy row with all the elements, cost elements being 0 and the supply being the difference between summation of B's minus summation of A's. Okay, so in that case we have to add a dummy row with all the cost element being 0 and the supply being the difference between B's minus summation of A's. Similarly, if the total supply is more than the total demand, that means A side, summation of A's is coming to be more than summation of B's. In that case, yes, definitely we have to add a dummy column so as to balance the matrix. right? When we add a dummy row and dummy column, all the cost elements to be considered are 0. So let's have a brief glimpse of the steps of northwest corner method. The first method, which is the poorest method. So step 1 is ensure that the matrix is a balanced one. This step we have to follow irrespective of what method we follow, because that is a requirement, right? That is the basic requirement for doing a or solving a transportation problem. Second step is select the upper left corner, that is the northwest corner, and that is the reason its name is northwest corner method. So select the upper left corner of the transportation matrix and allocate as much as possible to that cell. Adjust the associated amounts of supply and demand accordingly. Okay. Step 3 is if the row supply becomes 0, cross out the row and move vertically, because if you cross out the row, you cannot move horizontally, so you have to move vertically. And similarly, if the column demand becomes 0, cross out the column and move horizontally, as we cannot move vertically. By any chance, if both the column demand and row supply become 0, then cross out both the column and both the row. So we cannot move neither horizontally nor vertically. In that case, we have to move diagonally. Okay. And finally, continue step 2 until all the locations is met in the southeast corner of the transportation matrix. We will follow these steps and we will solve a problem so that it is easier for you to follow what I just said just now. Okay. So let's take a problem. First step, as we have done, check whether the problem is balanced. So you add the supply 20 plus 28 plus 17, that gives you 65. And this side, if you add these demands, that also gives you 65. So the problem is balanced. You have to show it accordingly, like this, that the problem is balanced. Once the problem is balanced, since we are following the northwest corner method, we will start with the northwest corner. Okay. So our problem is balanced. So let's start the northwest corner method. Now tell me, we'll start with this cell because this is the northwest corner cell. What is the corresponding supply? Supply is 20. What is the corresponding demand? Demand is 21. Okay. Now can you tell me how much I can allocate to this cell? Yes, it should be the minimum of these two, 20 and 21. So minimum is 20. So I will be able to allocate 20. You may ask this reason, why such so, right? It's very simple. Suppose you have got 20 rasgullas in front of you and you can eat only 10. So how many you will be eating? 10 only, right? Or the reverse. You can eat 20, right? And you can eat 20, but in front of you it's 15. So how many you will eat? Although you can eat 20, but since only 15s are available, so you will be having 15, right? So what I'm saying is, if out of supply and demand, whichever is minimum, that many only we will be able to allocate to this particular cell. So here we will be allocating 20 because the minimum of 20 and 21 is 20. So we will be able to allocate 20. Once we allocate 20, we will be adjusting the supply and demand accordingly, right? So 21 becomes 1 and 20 becomes 0. Once the supply becomes 0, we are going to cross out that particular row, as we said. So we will cross out this. Okay. Next. So I cannot move horizontally, so I will be moving vertically. So definitely I will move to this, right? I have just shown here. See 20. So here demand is 1 and availability is 28. So how much I will be able to allocate here? 1, minimum of the 2. As I allocate minimum of the 2, that is 1 to this cell, your demand becomes 0 and your supply becomes 28 gets reduced to 27. Once the demand becomes 0, I'm going to strike out the particular column, right? So this is how. Next, since the demand has become 0, I have crossed out the particular column. I cannot move vertically, so I will be moving horizontally. Now, if you move horizontally, what is the supply? Supply is 27, demand is 25. Yes, I hope you got the answer. So how much to allocate here? It's the minimum of these two, that is 25. So I will be allocating here 25. Right, so I will be allocating here 25. Once we allocate 25, the supply and demand are to be changed or adjusted accordingly. So we have done that. We have done so. 25 becomes 0. 27 gets reduced to 2. Once this becomes 0, cross out the entire column. So we cross out the entire column. Since we cannot move vertically, we will be moving horizontally. So we will come here. Here the supply is 2, demand is 19. I'm sure the answer you have got. So how much to allocate to the cell? 3. It's 2, right? So we will be allocating 3 to this. We will be allocating 2 to the cell containing the element 3. So supply becomes 0 and the demand becomes 17. Demand becomes 17, supply becomes 0. And finally, so we cannot move row wise, right? Horizontally we cannot move, so we will cross out this. And finally we are left out with only one cell. So supply is also 17, demand is also 17, so we will be allocating 17 to this particular cell. So once we allocate, we find that all the supply gets reduced to 0 and all the demand gets reduced to 0. This will be possible only when we balance the matrix. That means total supply, if it matches with total demand, then only all demand will get reduced to 0 and all supply will get reduced to 0 after our allocations. Right? Hope you have understood. So if I ask you, what we have found out? These are nothing but Xij. Xij means quantity transported from a particular source to a particular destination. So that means 20 was the supply. So all these 20 were supplied to warehouse 1. In case of P2, the supply was 28, out of which 1 was supplied to warehouse 1, 25 was supplied to warehouse 2, and 2 was supplied to warehouse 3. And in case of P3, total supply was 17, which was totally supplied to the warehouse 3. Once you get the answer, you can verify whether you have done correctly. As you can see 20, so all 20 are here. Summation should match with the total supply, right? 25 plus 1 plus 2, that gives you 28. 17 is matching. Column wise also it should match. 20 plus 1, 21. 25 is here and 17 plus 2, 19. So 19 demand has been met. So this is how we get the solution by Nordquist-Quander method. This is the initial solution, and the total transportation cost, as you can understand, 7 is the transportation cost to transport a single commodity from source P1 to warehouse 1, W1. So to transport 20 units, I will be needing 20 into 7, that is 140. So that way we have to add them together to get the total transportation cost. So my total transportation cost becomes, so these are the plants, these are the warehouses. So this we have seen, and this we do calculations 20 into 77 plus 5 into 1 like this to get the total transportation cost as rupees 462. Okay. This is how we get the solution by Nordquist-Quander method. Now let's see the next technique, that is least cost method. Now what are the steps of least cost method? Let's see that. First, like any case, any technique, we have to get the matrix a balanced one. Now select the cell with the least cost per unit transportation cost and allocate as much as possible to that cell. Adjust the supply and demand accordingly. Eliminate the row or column in which capacity or requirement is exhausted. So cross out the row with the supply 0, or cross out the demand with the cross out the column with the demand 0, right? And these steps are to be repeated until we get the solution. So we will take the same problem and we will see if we apply least cost method, what answer we get, right? So again we have taken the same matrix. We find that yes, the matrix is balanced 1, and then let's proceed. So here, since we are going by least cost technique, which is the least cost in the given matrix? So these are the supply, these are the demand, right? So out of all the Cij, what is the minimum cost? As we can see, this is the minimum cost. So allocate as much as possible to this cell. Now what is the demand? 19 is the demand and supply is 28. So definitely we can allocate the minimum of these two to this cell, right? So we can allocate 19. Once we allocate 19, this becomes 0 and this becomes 9. So let's see. So this becomes 0, this becomes 9. Once this becomes 0, I will cross out this particular column. Because once all this 19 has been allocated to this cell, we cannot allocate anything to this cell or this cell. So this entire column is to be striked out. That's what we have done. Next is out of the remaining, which is the lowest cost cell? Yes, it is 4. It is 4. So allocate as much as possible to this 4. So 17 and 21, minimum is 17. So I will be able to allocate 17 to this cell. So once I allocate 17 here, the supply and the demand are to be changed or adjusted accordingly. So we do so. 21 gets reduced to 4, 17 gets reduced to 0. Once 17 gets reduced to 0, I'm going to strike out the entire row, right? So that's what we have done. Now coming to this, which is the total, which is the smallest transportation cost? 5 is the smallest transportation cost out of available. So we will allocate as much as possible. So again, 4 is the demand, 9 is the supply. So how much you can allocate? The minimum of the two, that is 4. So we have allocated 4 here. And then supply demand are to be adjusted. 4 gets reduced to 0, 9 gets reduced to 5. Once it gets reduced to 0, I'm going to strike out the entire column, and that's what we have done. Right? Now we have got only one column with 2 rows. So what is the minimum? 6 is the minimum transportation cost. So allocate as much as possible. How much you can allocate? 20 and 25. So I will be able to allocate here 20. So we allocate 20. 25 gets reduced to 5. 20 gets reduced to 0. Once 20 gets reduced to 0, I'm going to strike it out. And then finally, we are left out with 7. Supply is 5. Demand is 5. This particular 5 is to be allocated here. So we allocate that. 5 gets reduced to 0, and finally the supply of 5 also gets reduced to 0. So at the end we have to ensure that all my supply gets reduced to 0 and all my demand gets reduced to 0. So here, what is the total transportation cost? It will be 20 into 6 plus 5 into 4 plus 7 into 5 plus 3 into 19 plus 4 into 17. Right? That means no goods were transported from plant P1 to W1. Similarly, no good has been transported from P1 to W3. So all the goods which were produced at P1, factory P1, is supplied to warehouse 2. So that is how we did this solution. So let's see what is the total transportation cost comes if we apply least cost method. So if we do so, we get total cost is 300. So by northwest corner method, my solution, my answer was 462, which got reduced to 300 when I applied least cost method. Now let's see the best method. If nothing is mentioned, you are always going to follow the best method, that is the VAM method, because it is going to give you the best solution. Okay, so let's see the steps. First, transportation matrix is a balanced one. Second, calculate the row penalty for each row by taking the mod value of the difference between the lowest cost and the next lowest cost. So lowest cost is what? In the particular row, what is the lowest cost that we have to find out, and in the same row, what is the next lowest cost? The difference of the two will give you the row penalty. Similarly, we have to calculate the column penalty. Column penalty means taking the difference between the lowest cost and the next lowest cost element in a particular column, ignoring the sign. Identify the row or column with the highest penalty, and in that particular row or column, look for the cell with the lowest cost. Allocate as much as possible to that cell and adjust the supply and demand accordingly. So same thing here. If eliminate the row or column in which capacity or requirement is exhausted or becomes zero. And finally, we have to repeat steps 2 to 5 until all capacities are exhausted. All supplies are exhausted to meet the requirements or the demands at various destinations. At the end, all the supplies and all the demands are bound to get reduced to zero because we have already balanced the matrix before we proceed for its solution, right? So let's take up some. Let's take an example. We have taken the same example, and we have kept the same example just to show you that how the solution is getting improved once we move from northwest corner method to Vogel approximation method. So this is a matrix. So first we will calculate the penalty. Now in this case, my first row, what is the penalty? Lowest is 6, next lowest is 7. So what is the penalty? Yes, the difference between the two, that is 1. So we have taken 1. Second row, what is the penalty? 5, 7, 3 are the elements. So lowest is 3, next lowest is 5. So penalty is 2. Third row, 4, 5, 8. So lowest is 4, next lowest is 5. So penalty is 1. In this case, what is the penalty? 4, 5, 7 are the elements. So minimum is 4, next minimum is 5. So penalty is 1 again. Then for the W2 column, it's 5 again, 1 again, difference between 5 and 6. In the W3 column, the difference between 3 and 8, lowest and the next lowest, that is 3 and 8, and hence the difference is 5, right? So once we calculate the penalty for the rows and for the columns, we have to identify the row or column having the highest penalty. In this case, the highest penalty is, yes, it is 5. So identify the highest penalty. Once we identify the particular row or column with the highest penalty, we will concentrate in that particular column or row only. So here W3 has got highest penalty. So we will be concentrating on W3 column only. All these are cost figures and we would like to minimize the total cost. So in this W3 column, which is the lowest cost element? 3. Yeah. So allocate as much as possible to this cell containing 3. How much you can allocate here? 19 and 28. So I can allocate here 19. I hope you understand. So first we will calculate all the penalty and then we will look for the highest penalty. So highest penalty in this case is 5 for the column W3. Once the highest penalty column or row has been identified, we will concentrate on that row or column. In this case, it is W3. So we will concentrate on W3 elements only. In this W3 element, which is the lowest cost element? 3. So we will allocate as much as possible to 3. Right? So we can allocate here 19. Once you allocate here 19, the corresponding row and column or the supply and demand are to be adjusted accordingly. So we have done so. Once the demand or supply becomes 0, we will strike out that particular row or column. In this case, my demand is getting reduced to 0, so I'm going to cross out the entire column, right? So we have done so. Next, we will calculate the second penalty. So penalty 2, penalty 1 I have not shown, but when you do it when you do it in your copy, then I will suggest that you don't need to draw the matrix again and again. Draw the same matrix and keep this penalty here, so that you can write penalty 1 and then penalty 2 like this. All the penalties are to be written on the right hand side of your matrix, and all the column penalties to be written at the bottom of your matrix. Okay, so penalty 2, difference between lowest and the next lowest, that is 1. Okay, we have calculated all the penalty, taking the difference between the lowest and the next lowest. For this we don't have to calculate the penalty because this is already gone, right? We have striked it out. Now out of this, which is the highest penalty? Yes, this is 2 is the highest penalty. So we have the P2 row having the highest penalty. Once we have identified the row, in this particular row, which is the lowest cost element? 5 is the lowest cost element. So allocate as much as possible to this 5. How much you can allocate here? 21 and 9. Right? 21 is the demand and 9 is the supply. Definitely I can allocate here minimum of the 2 and hence 9. So highest penalty. So concentrate in this particular row. In this particular row, lowest is the 5 element. Right? All these are cost figures. So I would like to minimize the cost. So lowest cost figure is 5. So allocate as much as possible to this 5. We have allocated 9 and change the demand and supply accordingly. Once the supply or the demand becomes 0, we will strike in the corresponding row or column. So in this case, we will cross out the second column, second row. Right? Now, same thing. We will calculate the penalty again. That is penalty P3. So it's 1 dash 1 3 and then 1 and then again dash. So highest penalty is 3. Right? So we have identified the column with the highest penalty 3, that is W1. Now in this W1 column, which is the lowest cost element? 4. So allocate as much as possible to this 4. So how much you can allocate? Minimum of the 2, that is 12 and 17. So 12 we can allocate. Right? So we have allocated 12 here. Adjust the supply demand accordingly. Your demand becomes 0, supply becomes 5. Once demand becomes 0, strike out that particular column. And then finally we have got only one column. So stop calculating penalty when you have got only one row or one column. In this case we have only one column, so we will stop calculating penalty and allocate by the least cost method. So in this particular column, which is the least cost? 5 is the least cost, so we will allocate as much as possible to this 5 first. Once done, the remaining are to be allocated to this cell containing the value 6. So let's see. 5 we have done. 5 we have allocated here. So supply demand are to be changed accordingly. So it becomes 0. So we will strike out this particular row, right? So it's like this, and then finally 20 demand and 20 supply. This 20 is to be allocated to the cell containing 6. So we have here, right? And then adjust the supply and demand accordingly. So everything gets reduced. Your supply gets reduced, your demand gets reduced, and the total transportation cost in this case, it will be 6 into 20 plus 5 into 9 plus 3 into 19 plus 4 into 12 plus 5 into 5, and that gives you total transportation cost to be 295, which is much better compared to your knotless corner method, which is 462, and this cost method, which is 300. So it's a comparison. So always remember, if nothing is mentioned, you should always get your initial basic feasible solution by using BAM technique, because that gives you the best solution. Okay. Now, this is how we get the initial solution. Now, how to get the optimal solution. That is the best solution starting from the initial solution. For that, we will describe or we will discuss the modified distribution method, which is popularly known as Modi method. Okay. So first step is get the initial basic feasible solution. Now we can go for optimality checking by Modi method if and only if the number of allocated cell is equals to m plus n minus 1. What m stands for? M stands for number of rows, n stands for number of columns, right? If the number of allocated cell is less than m plus n minus 1, it's a case of degeneracy, right? In order to make the problem a non-degenerate one, identify the cell which satisfies two criteria, that is lowest unit transportation cost and does not form a closed loop. This may be a little bit difficult for you to understand. Don't worry. In today's class, we are not going to discuss the degenerate problem. We are going to discuss a non-degenerate problem where number of allocated cell equals to m plus n minus 1. We will discuss the case of degeneracy in a separate video. So, just to start, we will take a easier case, that is a non-degenerate initial basic feasible solution, and see how to understand whether the solution is optimal or not. Okay, I hope you understand this. So we will be able to apply Modi method only when my number of allocated cell equals to m plus n minus 1, where m is number of rows and n is number of columns. Now if the number of allocated cell equals to m plus n minus 1, it is much easier, and such solution is called non-degenerate initial basic feasible solution. But if the number of allocated cell is less than m plus n minus 1, it is called a degenerate solution. We are going to discuss a degenerate solution in some other video, right? So let's discuss today the how to apply Modi technique when the initial basic feasible solution is non-degenerate. Non-degenerate, I repeat, it means that the number of allocated cell equals to m plus n minus 1. So what are the steps here? First, if we find that yes, the number of allocated cell is m plus n minus 1 and we can apply Modi method directly, in that case first is find out the row multiplier and column multiplier for each row and each column by using the formula ui plus vj equals to cij. And for unallocated cell, you calculate the cell evaluation, that is using the formula cell evaluation equals to Cij minus summation of ui plus vj. If all the cell evaluations, right, so first we have to calculate the ui and vj's equal to Cij, and that formula is valid only for the allocated cell. Once you get the values for all ui and all vj's, next is you have to calculate the cell evaluation for the unallocated cells. And if all the cell evaluations are non-negative, mind it, non-negative, optimal solution is reached. When I say non-negative, it covers both 0 and positive. So when all the cell evaluations are either 0 or positive, we say that the optimal solution is reached. So we will take another example and show how this modified distribution method can be applied, right? Okay. Now, if all the cell evaluations are non-negative, optimal solution is reached. But by any chance, if the cell's evaluations are negative, some of the cell evaluations are negative, in that case, select the unallocated cell with the most negative cell evaluation, right? Draw a closed loop starting from this cell and ending to this cell such that each corner point is being occupied by an allocated cell. If you remember linear programming problem, in case of linear programming problem, where the objective function is to minimize the objective function z, the entering variable is 1 with the most negative coefficient in the Cj minus z0. So in case of transportation problem, the cell evaluations, what we find out, they are nothing but the elements of equivalent to the elements of Cj minus z0. So in case of transportation problem, which otherwise if not mentioned is a minimization matrix, minimization problem. So if any cell evaluation is coming to be negative, that means it wants to come into my solution. It acts as a entering variable. Now if there is an entering variable, definitely there should be a leaving variable, right? Right? So if there is a leaving variable, then we should find out which variable should leave, and for that reason we will look for a closed loop. Always remember, closed loops are drawn to identify the leaving variable, right? And if we want to increase the number of allocated cell, then we should not look for a closed loop. This, what we say, will be much more easier for you to understand and comprehend once we take an example. Okay, find the new allocation so that allocations in each cell is greater than equal to 0. Always remember that allocation in each cell has to be greater than equal to 0. Allocations cannot be negative. I cannot say that I will be transporting minus 6 units from a particular source to particular destination, because that is absurd. So all the cell allocations has to be either 0 or positive, right? Repeat steps 3 to 5 until all cell evaluation values for the unoccupied cells are non-negative. That means the optimal solution is reached. So I have taken an example where we have got 3 factories or 3 plants and 4 destinations, D1 to D4, right? We have applied BAM technique to get the initial solution, but we have not shown here how to get BAM, because in this video only we have shown you how to apply BAM. So I'm sure you will be able to apply the same techniques and you will be able to get the initial solution which we have put over here. So it's like this. After getting the initial solution of by BAM, you will find that these are the allocations, right? So that means my total transportation cost is 2 into 1 plus 3 into 5 plus 1 into 1 plus 9 into 1 plus 15 into 3 plus 5 into 6, and that comes to be 102. Okay. Now in this case, how many rows we have? That is small m. How many rows we have? We have, no, I'm not able to write here. Sorry. In this case, how many rows we have? We have 3 rows, P1, P2, P3. So that is small m is 3. And how many destinations we have? 4. That means n, small n for Nagpur is 4. So m plus n minus 1 is 3 plus 4 minus 1, that is 6. How many allocated cells we have? 1, 2, 3, 4, 5, 6. So number of allocated cell equals to m plus n minus 1, and hence it is a non-degenerate solution, right? If it is a non-degenerate solution, then it is much more easier to solve if it is a degenerate solution. So into this class, as I have said, I will be discussing on how to solve a non-degenerate basic feasible solution to get the optimal solution. So my initial solution gives me a transportation cost of 102. This I will suggest you to remember this figure, right? Next. So that's what we have mentioned. 1, 2, 3, 4, 5, 6. Number of allocated cell is 6. M plus n minus 1 is also 6. M stands for rows and n stands for columns. Since number of allocated cell equals to m plus n minus 1, it's a case of non-degeneracy and Modi method can be directly applied. Next, once we understand that yes, Modi method can be directly applied, we have to find out the use for the rows and B's for the columns. Okay, in order to find out the U's and the V's, your number of allocated cells should be equal to m plus n minus 1. If it is less than m plus n minus 1, that is number of allocated cell is less than m plus n minus 1, then you will not be able to get all the values of the U's and the V's. You will get stuck up, right? So before you proceed in Modi's getting the optimal solution by Modi method, first you have to ensure, yes, the number of allocated cell is equal to m plus n minus 1. So yes, in our case it is holding so. So what I'll do is, we can assume any of this multiplier to be 0. I have got an advice. You look for the row or column which has got highest number of allocation and assume the corresponding multiplier to be 0. In this case, like in the first row we have got 2 allocations, in the second row we have got 1 allocation, in the third row we have got 3 allocations. Similarly, column wise, if I go 2 allocation, first column, second column 1 allocation, third column 1 allocation, fourth column 2 allocations. So highest number of allocation is in the row 3, P3. So we assume the corresponding multiplier U3 to be 0. You can assume any of the multiplier to be 0, but if you do so, that means if you assume the multiplier of that row or column to be 0 which has got highest number of allocations, in that case you have to go for minimum number of computations, right? So what I said, for the allocated cell, the formula is ui plus vj equals to cij. So this is u3 is 0, right? For this is an allocated cell, this is an allocated cell, this is an allocated cell. So u3 plus v1, because this is with respect to column v1, right? So u3 plus v1 equals to unit transportation cost, that is 5. So what is the value for v1? Since u3 is 0, v1 is 5. Okay. Similarly for this is an allocated cell, same formula holds here. u3 plus v3 equals to unit transportation cost, that is 15. So since u3 is 0, v3 will be 15, and same way, since u3 is 0, v4 will be 9. Okay, so first what we'll do, we'll assume u3 to be 0. By mistake I have put all the multipliers in the matrix, but computation wise this is to be shown like this. First we will assume u3 to be 0 because the row p3 has got highest number of allocations. Once you assume u3 to be 0, then v1 will be 5. Directly we can write v3 will be 15, yes, and v4 will be, right, it will be 9. Now just see, if v4 is 9, can you calculate u2? Because v4, this is an allocated cell. This ui plus vj equals to cij. This formula is valid only for the allocated cell. That means v4, this is an allocated cell. Corresponding multiplier is what? v4 and u2, second row and fourth column. So v4 plus u2 equals to this one, unit transportation cost. So what will be u2? It will be, yes, it will be minus 8. Right? Because minus 8 plus 9 gives you 1, this one. Okay. Now, how to get the values for this? If both the values are not known, I will not be able to calculate. So first I have to get the value for u1 using this cell, because this is an allocated cell. So this cell means u1 and v5. So u1 plus v5, u1 plus v1, sorry, v1 equals to 5, right? So u1 plus v1 equals to 2. So if v1 is 5, what will be u1? Yes, it is minus 3. Right? Once you get the value for u1, you use this value to get the value for v2. So v2 will be minus 3 plus v2 equals to 3. So v2 will be plus 6. Right? So this is how we can get the values of all the multipliers u1, u2, u3 for the rows and v1, v2, v3, v4 for the columns. Next is we have to get the cell evaluations for the unallocated cells. That means these are my unallocated cell when there is no allocations, and we have to compute the value for the cell evaluations. So let's start with this. What will be the cell evaluation for this particular cell? u1 plus v3, that is minus 3 plus 15, that gives you 12. So 12 is to be subtracted from Cij, that is 11. So that gives you minus 1. Okay. Same thing here. How you will do it? This cell is belonging to first row, fourth column. So minus 3 plus 9, that gives you 6. And then 6 is to be subtracted from this 7, the Cij. So that gives you 1. Here, yes, you can try. It's minus 8 plus 5. That means minus 3. So 1 minus minus 3. That gives you 4. Here, minus 8 plus 6. That gives you minus 2. So 0 minus minus 2. That gives you 2. Here, it is minus 8 plus 15. That means 7. So 7 is to be subtracted from 6. So 6 minus 7, again we get minus 1. And for this, which is an unallocated cell, again we have to find out the cell evaluation. So 0 plus 6, that is 6. 6 is to be subtracted from 8, that gives you 2. Now the question is the solution optimal? Answer is no. I said solution is optimal when all the cell evaluations are non-negative. Here we have got two cells with negative cell evaluations, and hence the solution is not optimal, right? Solution is not optimal, as we can see here. So how to get the optimal solution? Now before we say so, I would like you to make one point to be noted very carefully, that see, when the cell evaluation is coming to be negative, what is the physical interpretation of that? The physical interpretation is, suppose I take this cell, so cell evaluation is minus 1. That means if I include this cell into my solution, my transportation cost, my total transportation cost is going to reduce by 1 for each allocation I make here, right? So if you put 6 allocation here, suppose 6 allocation here, because for each allocation your transportation cost, total transportation cost is going to reduce by 1. So your initial solution was 102. That's the reason I have asked you to remember that figure. So that initial total transportation cost came to be 102, and suppose if you have got 6 allocation here, then 102 minus 6, because for each allocation my transportation cost is going to reduce by 1. So if I have allocated 6 here, so my total transportation cost is going to reduce by 6. So 102 minus 6, that gives you 96. In that case, I would have got 96. Okay. So suppose the allocation here is 1. In that case, what will happen? Suppose after working out, we find that the allocation here is 1. That means my total transportation cost decreases by 1 into 1. That is, it is going to reduce by 1. So earlier it was 102. So now we will get the solution as 101. So let's see whether what we are getting. Okay, excuse me. Now I would like to show you one more thing here. So this, out of these two cell evaluations are negative. That means they want to come into my solution. Now if both the cell evaluations have got the same negative value, I can choose arbitrarily any of the two, right? Now I have chosen in this case I have chosen this cell. Now if this cell wants to come into my solution, then how many allocated cells we will have? 1, 2, 3, 4, 5, 6. 6 we already had. This also wants to come into my solution. In that case, the number of allocated cell will be 7. 6 plus 1, 7. But is it allowed? No. At any given point of time, your number of allocated cells should be always equals to m plus n minus 1. That is 6 in our case. So if that is so, if this wants to come into my solution, someone from this allocated cell should leave, right? Who will leave? Which cell will leave? Which allocated cell we should consider for leaving? For that, we have to draw a closed loop. So that's what we have drawn, a closed loop. Closed loop means it's a loop which will start from this point, because this wants to come into my solution, and it should come back to the same point, and it is composed of horizontal and vertical lines only, and each corner point of the closed loop or the horizontal and vertical lines should be occupied by an allocated cell, right? So what is the definition of closed loop? A loop that starts from a given point and comes back to the given point, with all the corner points being occupied by allocated cell. This is an allocated cell, this is an allocated cell, this is an allocated cell. So all corner points should be occupied by an allocated cell, and it is composed of only horizontal and vertical lines, right? So that means if this wants to come into my solution, out of this 3, one should leave. Now which one will leave? That again depends on computations. So let's see. Now let's suppose this wants to come into my solution, and I assume that x units to be transported through this route. So if you want to transport x units through this route, then definitely this allocation should be 1 minus x, this allocation should be 6 plus x, and this allocation should be 3 minus x. Alternative, negative and positive, because total demand finally cannot exceed, in this case my total demand in the first row was total supply in the first row was 6. So if you have allocated x here, it has to be subtracted from here, so that total supply remains 6 only. Okay, so if you have allocated x here, it has to be subtracted from here, it has to be added here, and it has to be subtracted here, so that your allocation becomes this. Now these are the allocations. So can your allocations be negative? Definitely not. X is a positive quantity, so 6 plus x will definitely be a positive quantity. But what about 1 minus x and 3 minus x? They may take negative values which they are not supposed to take, depending on the values of x. So we should consider the value of x in such a way that 1 minus x and 3 minus x can never be negative. That means 1 minus x has to be greater than or equal to 0, 3 minus x has to be greater than 0. If both the conditions are to be satisfied, what is the maximum value of x? The maximum value of x is, out of these two, whichever is minimum. So maximum value of x is 1. That means this becomes 1 now. This is an allocated cell with its allocation being 1. This is 1 minus 1. That means this is a free cell now. This is 6 plus 1. That is 7 items are allocated through this route, and this gets reduced to 2. Right? So with this, our new matrix becomes this. 1 is allocated here. This got free cell. This became free cell. This becomes 7, and this become 2. So this became 2. So here your cell evolution was minus 1. How many units you have allocated to this? 1. So your total transportation cost will get reduced by 1 into 1, that is 1. And earlier your total transportation cost was 102, and now the total transportation cost, which you calculate by summation of the multiplications product, summation of the products, that is 3 into 5 plus 11 into 1 plus 1 into 1 plus 9 into 1 plus 15 into 2 plus 5 into 7, and that gives you 101. Right? Once you get this, again we have to do the same steps again and again until and unless we get all the cell evolutions to be non-negative. So again we start with the row having the highest number of allocations, that is U3 is 0, we have assumed. So if U3 is 0, definitely I am sure now you will be able to tell me the values of V1, V2, 3 and V4. Yes, V1 will be 5, the Cij value, V3 will be 15 and V4 will be 9. So that's what we got it here. Once this is known, again we calculate the value of U2 because this is an allocated cell, right? This formula Ui plus Vj equals to Cij is valid only for the allocated cell. So I should look for allocated cell. This is an allocated cell. V4 is known. So corresponding U2 will be -8 because summation is coming to be 1, right? This one. So it is -8. And what about this? V3 is 15. If V3 is 15, what will be U1? U1 will be -4 again. So -4. So if U1 is -4, what will be V2? -4 plus V2 is 3. So -4 plus 7 will be 3. So V2 becomes 7. Right? So once you do so, again we have to find out the cell evaluation for the unallocated cell. Unallocated cell. These are called unallocated cell where there is no allocations. And we compute that using the same formula Ui plus Cij minus Ui plus Vj. Right? For example, for this, how to calculate? This is -4 plus 9, that is 5. 5 is to be subtracted from 7, so that is 2. So that is how we got it. Same thing, we will calculate the cell evaluations for other unallocated cells also, and we find that still one allocation is there, one cell evaluation is there which is negative. This negative means what? This means this particular cell wants to come into my solution. If this particular cell wants to come into my solution, then one should leave out of the allocated cells, right? Now, if this cell come into my solution will get improved by 1 per allocation. So if I have allocated 1 here, then my total cost will get reduced by 1. So earlier it was 101, total transportation cost was 101, right? Now if we allocate something over here, then suppose I have allocated 1 here, then my total transportation cost will reduce by 1, that is 101 minus 100, 101 minus 1, that is 100. So whatever we get, let's see. So this wants to come into my solution. So if this wants to come into your solution, you should look for a closed loop. Always remember, closed loops are drawn to find out which will be your leaving variable. So 6 number of allocated cells are there. This also wants to come into my solution. In that case, number of allocated cell will be 7, which is more than m plus n minus 1, that is 6. So that is not possible. So if this wants to come into my solution, someone out of the allocated cell should leave. So for that, again we have to draw a closed loop. Who will leave? Closed loop will be horizontal, composed of horizontal, vertical and horizontal lines. So this is the closed loop. As you can see, each corner point being occupied by allocated cell. Now suppose you allocate x here. So if you allocate x here, I'm sure you will be able to tell me this allocation will get reduced to 1 minus x, this will be 1 plus x, and this will be 2 minus x, right? So that's what. Again the same thing, 1 minus x and 2 minus x, they cannot be negative, so both are to be greater than or equal to 0. If both the conditions are to be satisfied, what is the maximum value of x? It is 1. So it is 1 minus 1, that means 0, that means it becomes a free cell. Here the allocation becomes 1 plus 1, that is 2, and their allocation becomes 2 minus 1, that is 1, right? And this is 1. So my new matrix becomes this. Once I get this, although it's a big sum, right, but the computations are very easy. Once you understand the method or the technique, you will be able to do it very fast, but maybe a little bit lengthy. So once we get the new allocations, again we will calculate the u's and the vj's very fast and see whether the cell evaluations are coming negative. So u3 equal to 0. So once u3 is 0, v1 equal to 5, v3 equal to 15, v4 equal to 9. Once we do so, so in this here no allocations. So in this column there is an allocations. So V3 is 15. So can we find out the value for U2? So V3 plus U2 equals to 6. So what is the value of U2? It's minus 9. Similarly, I can take the help of this column to get the value for U1. So V15 plus U1 equals to 11. That means U1 equals to minus 4. So once you get the value for U1, what will be the value for D2 or sorry B2? It will be minus 4 plus something equals to 3. So minus 4 plus what will give you 3? It will be V2 equals to 7. Right? So once you get all the values for U's and the VJ's, we will find out the cell evaluations for the unallocated cells. So for this cell, it will be, it will be minus 4 plus 5, that is 1. 1 to be subtracted from 2, that gives you 1. Yes, can you tell me for this? First you get the value and then verify from the video. So it will is, minus 4 plus 9, that is 5. 5 to be subtracted from 7, that is 2. Like this, we calculate the cell evaluations for all the unallocated cell. And since all the cell evaluations, as you can see, are non-negative, right? It can be 0, it can be positive, but if they are non-negative, so optimal solution is reached. So the optimal solution is reached, and just see here we have allocated 1 unit to this particular cell, and the cell evaluation was minus 1. So compared to earlier transportation cost, which was 101, my now transportation cost gets reduced by 1. So my new transportation cost, even you don't calculate it separately, it is, you can say with surety that it is going to come to be 1 less than what a solution we got earlier. So earlier we got 101, 101 minus 1 into 1, that is 100. The same thing you can verify from the result, that is 5 into 3 plus 11 into 1 plus 6 into 1 plus 15 into 1 plus 9 into 2 plus 5 into 7, that is also going to give you 100. Right? So this is how we come to end of today's class, where we have learned what is the transportation problems, what are the steps to get the optimal solution of a transportation problem, what are the 3 techniques to get the initial basic feasible solution, which is the best initial basic feasible solution technique, that is VAM, and finally how to get the optimal solution using Modi method from the initial solution what we got from VAM. Right? So thank you for having your patience hearing. I hope you have learned this transportation, how to solve a transportation problem. Thank you and bye for today. Okay, so see you.